Hello everyone. In this video, we're just going to kind of introduce the notion of change of basis. This tends to be one of the more challenging concepts, so just an intro. I don't expect it to make 100% sense, but hopefully a decent bit. So first, let's do a very brief recap of how to do a matrix representation of a linear map. So if we have some f from v to w, and these guys have bases, say v1 down to Vn and W1 down to Wm, then the idea is we get an m by n matrix by taking the coordinate vectors of the images of the basis vectors. So here we basically just look at f of v1 down to f of vn. We want to see where the basis vectors go because we know that knowing the basis vectors is enough to tell us where everything goes. And then represent these in our basis for W. So take coordinate vectors of these things, right? Because f of vi is going to lie in W. And so take the coordinate vectors of the f of vi with respect to the basis of W. And that's how we get our columns. So we get our m by n matrix by taking basically, so let's call this b sub w for that basis. So our first column would be the coordinate vector for f of v1 in that basis. And then our nth column finally would be take the image of that nth basis vector of v and take its coordinate vector. Okay, so that's going to be an m by n matrix. So now we're going to use this for a very specific map when we're changing bases. So a natural question would be, why do we even care? Why do we want to change bases? I like my standard basis. It's nice. I don't want to change it. And that seems very reasonable in and of itself, but there are some reasons. So, if you're dealing with things in circles, trying to find integrating over a circle or something like that, circles are much easier to deal with in polar coordinates than in rectangular coordinates. So, for problems like that, you might want to change your coordinate system, change your basis that you're thinking about so that you're thinking in terms of polar coordinates as opposed to rectangular. This also works for something like this. So just think of this picture. So if you see this shape here, that's not necessarily super easy to describe. I mean, it's a rectangle, but it's on a tilt, right? It's not lined up with our normal axes. But if we change our basis so that our new coordinate axes are in blue, if we just perform this rotation and switch to new axes, then suddenly we basically just have the picture, boom. And then that rectangle is super easy to deal with, right? I can calculate that area real fast. I know all of these coordinates because, well, it's just lined up naturally with my usual axes. And in terms of matrix stuff that we're going to deal with, and by the way, these coordinate changes happen all the time in like physics, for instance. So they do actually happen a lot in the real world. Rotations are very common in the real world. In terms of matrices, we've seen these linear maps. We can often choose a new basis so that linear maps are described by even diagonal matrices a lot of the time. And in that case, if you're talking about matrix multiplication by a diagonal matrix, that is very, very easy to do, whereas by just some arbitrary matrix, that might be very complicated to do. So basically, we can make matrix algebra much easier. Okay, so first we're going to analyze how to change to the standard basis. So what do I mean by changing to a basis? So in this case, the idea is that we're not actually changing any vectors. So we're just doing R2 to R2 via the identity map, not changing any vectors. We're simply changing how they're represented. So basically here, we want to view this with basis B and then our target with basis E. So we're basically just taking the same vectors but then reinterpreting them in a different basis, okay? So in terms of finding a matrix that does this, it's going to be finding the matrix that represents the identity. So we want to find A for the identity map. And here I'm going to call it A, B, comma, E to represent that we're going from B, the basis B, to the basis E. And I'm always going to call our standard basis E in this case, mostly because we call the standard basis vectors like the little ei's, okay? So how do we do this? Well, if we're just trying to find a matrix for the identity map, that means we should find where the basis vectors for our first space go and then take their coordinate vectors, right? So we should find, well, what's their image? It's just going to be themselves, right? So we want to find the coordinate vector in E of 1, 1 and the coordinate vector in E of negative 1, 2. These will be our columns of A. And in this case, we're in luck because we naturally write things in terms of the standard basis. So I mean, 1, 1 is 1 times 1, 0 plus 1 times 0, 1. So it's just itself. And it's the same thing here. Anything written in the standard basis is just going to be itself again in terms of the coordinate vector. So thus, my A sub BE is going to just be 1, 1 for my first column and negative 1, 2 for my second column. And so this represents the identity map, but changing these bases, okay? All right, so now we want to see how to go back. So it was really easy to go to the standard basis. It is in general not quite as easy to go back because here, right, we'd be doing the opposite thing. So it's still the identity map from R2 to R2, but this time we'd be starting in the standard basis and ending up in this new basis. And so you would want the coordinate vector of 1, 0 in terms of 1, 1 and negative 1, 2, and the coordinate vector for 0, 1 as well. And so that's not as obvious, right? I mean, you can definitely solve for it, right? It would be a pretty quick process, but there's an easier way. And here we're going to use the fact that we know something about the identity. It's invertible, right? It's clearly a bijection. We already know it's linear. The fact that it's invertible means we have another way of going backwards. So if you think that going to the standard, right, A sub B comma E, this was representing the identity map. This went basically from R2 to R2, viewing this as B and this as E. How do you think we go backwards? Well, you want to undo what you did. Identity is invertible. It's going to be the inverse. So A from E to B, going backwards, is just A, B, comma, E inverse. And so it's just take that matrix from the previous example and take its inverse. And this just so happens to be, so you could just do the row reduction pretty quickly, or just plug it into an inverse matrix calculator and you would get this. And so this is the matrix that sends you back. And this tells you what the coordinate vectors are. So the coordinate vector for 1, 0 here would just be that first column, so 2/3, negative 1/3. And the coordinate vector for 0, 1 would be that second column, so 1/3, 1/3. And you could check that those work as well if you want to. Okay, so now I want you to try one on your own. So again, we'll have the standard basis be one of them and this other basis B. And so I want you to find both A from B to E and A from E to B. So we've already talked about how to deal with going to the standard or from the standard, but what if neither is the standard, right? So what if you've got some B1 here that's like U1, U2, and B2 that's V1, V2, these are both bases of R2, then how do we change from one to the other, right? I mean, again, you could just do the coordinate vectors, of course, and that would just be some matrix computations, but we can also leverage what we already know. And so the idea is as follows. We can use E as the middleman. So we can first take our first basis to the standard basis, and then, because we know how to go to the standard, and we also know how to go from the standard. And so then we take that to B2, and so that composition will be this. So this guy would be a sub b1 to e, and then this would be a sub e to b2, or as we know from that previous example, right, this is just, because it's easier to go to the standard, b2 to e inverse. And so let's do a quick little example here to show how this would work. So let's consider these two bases. So the first one, right, so a b1 to e, that's easy, right, because we're going to the standard basis. And so this is just slap those guys in there. They are already in coordinate vector form. And then our a, we don't really want to think from the standard. We want to think to the standard, but it's inverse. And so this guy's inverse is just going to be, well, put those columns in already, and then take its inverse. And then what order are we actually doing these? So we go to the standard first and then down. And so again, we want to multiply on the left each time. And so it's actually going to be -1, 2, 1, 0. And then on the left, we want to multiply by this guy's inverse. Okay. So you want to think like function composition, we're going inside out. And so this just so happens to be -1/2, -1/2, -1, 1, if you're interested. And so for your second exercise, I want you to try doing something similar. So take this first basis to this second basis, find that matrix where neither of these is the standard, but you should kind of use the standard as a middleman. Thank you for watching.